Hello. In this video, we're going to look at some more min-max problems. In particular, we're going to start with one that involves cost. So an open top rectangular box is to have a volume of 250 centimeters cubed, and the width of the box is to be 5 centimeters. If the cost to build the base of the box is $2 per centimeter squared, and $1 per centimeter squared for the sides, find the dimensions of the box so the total cost to build such a box is minimum. Now again, just to help you understand the problem here, of course, you want to find the minimum cost when building something because you want to save money as a company. You'd never want to find the maximum cost. That would be silly. And if you think about it, the base of the box makes sense to be more per centimeter squared. If you're building a box, the weight is carried by the base. And so the sides need to be strong, but the base tends to be stronger. If you look at a packaging box you get from a store, the base tends to be reinforced so it can hold that weight. So the base of the box is going to need more material, or it needs to be made of a stronger material, which is why it will cost more. So let's start with a diagram here. So we have a box. So we draw ourselves roughly some kind of box like this. Now the box is said to have, maybe we'll move this over just a bit. There we go. Now the box is said to have an open top. So I tend to just kind of draw it like that so it looks like it's open. Or you can say that the top is open. Open. And we should give it some labels, maybe X, Y, and Z. So we want to find the cost. So cost, this is what we want to minimize. Now we're going to need a function for cost for sure before we are able to minimize something. But maybe I'm going to jump at the volume first. I like the volume formula. It's given to me right at the beginning, and so I'm going to write that V is equal to X, Y, Z, and so 250 is equal to X, Y, Z. That equation is definitely going to be useful to me as I look at trying to change around the formula for the box. Now, I did label it X, Y, Z, but notice we have an important piece of information here. We are told that the width is going to be 5 centimeters. So we don't actually want to have this extra variable y here because we're told that the width is 5. And so by adding the y there, we get too many variables in our setup. And so it's much better to say, okay, this is going to be x times 5 times z. Or we could say, if we divide both sides by 5, we'll get 50 equals xz. We don't want to go adding extra variables if we don't have to, because eventually we're trying to just get down to one variable. And so 2 variables is already a lot, 3 is too many. Now let's try to find a function for cost. So C, well, we're going to pay $2 per square centimeter on the bottom. So we're looking at surface area, and the bottom is going to have an area of 5 times x. Then we're going to pay $1 for the sides. So if you notice, there's a front and a back. So that's going to be xy. So there'll be xz, sorry. So xz for the front and xz for the back, so 2 of them. So this is front and back. And then we're also going to have the right and left side. So that's going to be z times 5 in terms of an area. So cost of 1, 5z, and then 2 of them. And so this is the sides. Alright, so let's simplify that a little bit. So cost is equal to 10x plus 2xz plus 10z. Now we have to figure out what we want to get rid of from this, and you're more than welcome to substitute in for x or substitute in for z. It doesn't really matter to me, but one of these has to get rid of because we need cost to be a function of one variable. So because there's because I want to just do a different one, I'm going to solve for x and then we'll put in for z just for practice so we have a different variable in there. So here we'll divide by z, divide by z, and x equals 50 over z. So I'm going to take that as x and plug it in over here and here. So that'll give me the following. Cost is equal to 10 times 50 over z plus 2 times 50 over z times z plus 10z. So again, let's simplify before we do calculus. So this is going to be 500 over z. This is going to, the z's will cancel, so plus 100. And then plus 10z. Alright, let's do the derivative. This will be minus 500 over z squared, because we have z to the minus 1. That gives you minus 1z to the minus 2. The 100 goes away because the derivative of a constant, of course, is 0. And then we get plus 10. Now again, we're always trying to set this equal to 0, which means we're going to need to do a little common denominator business. So this is over z squared over z squared. We need our proper sign diagram set up, so this will be minus 500 plus 10 z squared over z squared. We can do a little bit of rearranging and a little bit of factoring here. So 10 will factor out, z squared minus 50, which will give you 10 z minus root 50, z plus root 50 over z squared. Alright, let's draw our sign diagram. So over here, we're going to have a lot of information on this. We've got undefined at 0, got roots at 50, square root 50, and negative square root 50. So pick a number bigger, we're going to get positive. So positive, negative, positive. Oh, this is an even. Negative, positive. So we have increasing, decreasing, decreasing, increasing. Now again, it's tempting to think that there might be a minimum cost over here, somewhere over here. Of course, it looks like the minimum cost is here, but you can't fully justify that if there's still a decreasing portion here, or it's coming from a small part over here. But again, if you think about it, these are z values, and of course, the domain of z. So the domain of z would be, well, 0 to infinity. You couldn't have a negative value for z. That would be ridiculous. So all of this gets crossed off because it's not in the domain. Not in the domain, which means we have ourselves a relative minimum at z equals root 50. So therefore, rel min at z equals to root 50, which at this point we should probably simplify it. Root 50, there's a 25 in there, so we could get 5 root 2, right? Because we would have just over here root 50 equals root 25 times root 2, so then 5 root 2. Alright, so we can find the information that we need. They want the dimensions, so we should find the other dimension, which would be our x. X is equal to 50 over z. So we get 50 over 5 root 2. So 10 over root 2, which we could then rationalize. So root 2, root 2. So we'll get 10 root 2 over 2, which is also 5 root 2. This is something you'll find is common when you're doing min-max problems. Sometimes there's a bit of symmetry that comes up, and so in this case, the optimum dimensions were x and z being equal to each other. They were both 5 root 2. So our final answer, the dimensions that minimize cost are 5 root 2 centimeters, 5 root 2 centimeters, and of course the original 5 centimeters that they gave you. And there's our solution. Next example, let's find the points on the graph y equals 4 minus x squared that are closest to the point 0, 2. How would we do this one? Well, let's start with the diagram. At least we know that there's a graph, so we can draw a graph here. Our parabola will look something like this. It's up at 4, and then opening down. And we have another point at 0, 2, so we could draw that in here. And, well, we're trying to figure out where on the graph that distance is going to be the smallest, when it's going to be closest. We don't know where on the graph that is, so let's call that point xy. But we do know this point over here, this is 0, 2. Now we need to find the distance, and hopefully you remember your distance formula from grade 10 pre-cal. If not, feel free to watch a video on it. Just Google the distance formula Khan Academy and something should come up. But the distance formula is this. If you want to find the distance, you take the square root of, it would be like x2 minus x1 all squared plus y2 minus y1 all squared. It actually comes from the idea of the Pythagoras' theorem, and so what you're doing is you're creating a little mini triangle here inside your picture, and you're doing x2 minus x1 to find this side of the triangle, and y2 minus y1 to find this side of the triangle. Then you're squaring them and square rooting them to get this total distance d along the outside, because of course Pythagoras says a squared plus b squared equals c squared. So using our distance formula, we'll get d is equal to the square root. x2 would be x, x1 would be 0, so x minus 0 squared. y2 would be y, y1 would be 2. And so there we have it. This, which we could simplify a little bit, is x squared minus, or plus y minus 2 squared. This is what we want to minimize. But, well, there's a few problems. First off, of course, there's two variables, so we need to get rid of one of the variables, and what we can do is we know what y is equal to. This point here, xy, y is always on the graph, which means y is always equal to 4 minus x squared. So we're going to plug that in so we can get just one variable. So x squared plus 4 minus x squared minus 2 squared. So x squared plus will be 2 minus x squared squared. So we get x squared. We'll have to FOIL this out, so this will give us 4 minus 4x squared plus x to the 4. So if we clean that up, we'll get x to the 4 minus 3x squared plus 4. All right, now this is our formula for d, and we want to minimize this. And you are totally welcome to take the derivative of this, but if you do, notice there's a bit of chain rule going on here, right? We have this square root business that'll have to go to the bottom, and then you have to do the derivative of the inside. It's just a little bit messy. And so one of the things you can do with questions like this is you're actually able to minimize not just d, but you're able to minimize d squared. And so this is a bit of a trick you might want to know about. Here's our trick. This is a little trick to be aware of. Is instead of minimizing d, we're going to minimize d squared. Minimizing d squared and minimizing d will give us the same point at which the minimum occurs, but it will help our math a little bit. And so minimizing d squared just gets rid of the square root. So over here, d squared would be equal to x to the 4 minus, so x to the 4 minus 3x squared plus 4. But we don't want to call this like a d squared prime or something, right? That would look a little silly. If we were to write d squared prime, it looks like maybe d to the 21 or something, and so we don't want to write something weird like that. So we're going to call this thing a new function. We're going to call this fx. So let's do f prime x. That'll give us 4x cubed minus 6x, which is actually a very nice function. No square roots, no denominators, nothing crazy there. So here we go. We're going to factor out a 2x, giving us 2x squared minus 3. Then we can go ahead and factor out, well, we could do a difference of squares from that. So we'd get 2x, and then we get square root of 2x minus root 3, square root 2x plus root 3. And so we can go ahead and draw a sign diagram from that. A little tricky here, maybe I'll write the values. So this will be x equal to 0, x equal to root 3 over root 2. And then this is x equal to negative root 3 over root 2. Alright, so let's see what we get here. We've got 0. We've got root 3 over 2. You could combine them into one root. Negative root 3 over 2. So we pick a bigger number, say 10, we're definitely going to get positive. So positive, negative, positive, negative. So decreasing, increasing, decreasing, increasing. Now remember, we're trying to find the minimum, and it looks like it's happening here and here. Well, that's actually valid. In this case, we're going to get two minimums because the domain for x is all real numbers. So the domain for x is negative infinity to infinity. Because x is just a coordinate point on the graph, and you could have negative coordinate points. That's not a problem at all. So we're going to have two minimums. It's going to happen here and here. There's two places where we get a rel min. And that's totally good, because the symmetry of the parabola will actually show you that there's 2 points that are closest. One on the right side and one on the left. So let's go ahead and find our y values then for these. So we would have y equal to 4 minus, well, we'll do the negative one there first. So negative root 3 over 2 squared, which will be 4 minus 3 over 2, which would be, well, 8 minus 3 all over 2, so 5 over 2. And if we do the other one, y equals 4 minus root 3 over 2 with no negative, we'll get 4 minus the same thing, so 8 minus 3 over 2, so the same y value, 5 over 2. So what we get is that we have two closest points. So the closest points are, and we'll write them as coordinate points. So the one point is negative root 3 over 2, comma 5 over 2, and root 3 over 2, comma 5 over 2. And so there are actually two different points where we get that minimum distance, where you get the closest point. And again, that's fine. You can have minimums that happen, they have to be the same distance, of course, but you can have a minimum happening at two different points. So let's look at an example with a window. In this one, we have a window consisting of a semicircle on top of a rectangle. If the perimeter of the window is pi plus 4 meters, determine the dimensions of the window that will allow the maximum amount of light to pass through. Now, sometimes you get questions like this where they give you weird measurements for perimeter, but just trust that we actually need that pi to make the math work out nicely later. So it's a good thing that the pi plus 4 is the actual perimeter. You wouldn't want it to be something else. Usually they set these questions up so that the numbers work out decent, because of course you don't have a calculator when you're doing them. So we have a window with a semicircle and a rectangle. So here's our rectangle, and then a semicircle. Now we should give some measurements to it, and I'm going to start with the circle. So the circle has here a radius of r. And okay, well, the rectangle will have a height of h if we want, because we're talking about a window. We could call the bottom like x or length, but that would be an extra variable. Now we have 3 variables. It would be better to label the bottom in terms of r. So instead of labeling it x, is there a way to label it in terms of a variable we've already used? And if you look at the radius, well, the radius goes from the middle to one side and then another radius from the middle to the other side. So the bottom could actually be labeled as 2r, which is a much better way of labeling it. Now, again, we would like to label this portion here the top of the window because we're going to need perimeter. And the top of the window would have a length of half of a circumference. Circumference we know is 2 pi r. So this distance here from one side to the other side, that's going to be just pi r. So just pi r. Alright, so we can always start with whatever formulas we want, but eventually we need to figure out what we're trying to maximize. So I'm going to start with what we're trying to go for. We want to have the most light pass through, which means we're talking about area. So area, which would be equal to, if we look, we have the rectangle portion, which is 2rh, and we have the semicircle, which is pi r squared over 2. This is what we want to maximize. We want to maximize because we're trying to find the most light. That's how you make a window. You don't want the minimum light. If you ask your parents, they're going to tell you they want big windows to allow lots of natural light. It gives you the most amount of light possible. So we want the biggest area. But of course, there's 2 variables, so we should find another formula, in this case perimeter, and see if we can substitute a variable. So perimeter will be 2r for the bottom, and then 2h's for the sides, and then pi r for the top. And so we know the perimeter is equal to pi plus 4. It looks like it will be easier. There's an r squared and an r, so it looks like subbing in for r would be hard, but there's just an h. So I'm going to isolate for h because it looks easier to solve for. So I would get 2h equals pi plus 4 minus 2r minus pi r. So h is equal to pi plus 4 minus 2r minus pi r over 2. And so let's take that h there, and let's sub it in for our h. So that will give me area is equal to 2r times, well, I'll have pi plus 4 minus 2r minus pi r over 2 plus pi r squared over 2. And while, again, this is in terms of only one variable, we should try to simplify it before we get too far. So we'll cross off the 2's, and we could multiply in that r. Again, it will make your calculus easier if you do some algebra first. So we'll get r pi plus 4r. You could have called it, maybe I'll call it pi r there, just to be consistent. So I'll have pi r plus 4r minus 2r squared minus pi r squared plus pi r squared over 2. Now you are more than welcome to combine, of course, some of these. You could combine the minus pi r squared with the pi r squared over 2, but you don't have to combine all like terms because we're just trying to simplify a little bit. We're not trying to get as simple as possible. And so I think this is good. Let's go ahead and do the derivative. A prime. So the derivative of pi r, well, this is tricky. We're doing the derivative with respect to r, so that's going to be pi times 1, so just pi. 4r will be 4, minus 4r, minus 2 pi r, and then plus pi r, because the 2 will cancel with the 2 on the bottom. All right, time for some more simplification. So we get pi plus 4 minus 4r minus just a pi r, if we clean that up. All right, so we're trying to get that sign diagram, and we need to get this a little bit more Simple little bit of factoring. Might not be clear right away, but there's an r in common, and actually a negative r in common with the second two terms. So I'm going to factor that out, giving me 4 plus pi. Now if you notice, I have a 4 plus pi, or a pi plus 4 in common with both of these terms. Right? Pi plus 4, pi plus 4. So I'm going to factor that out. Or 4 plus pi, either way. Leaving me with, well, 1 minus r. Now if we set this equal to 0, of course this has no r in it, so that doesn't give me any factors, but this gives me r equal to 1. So for my sign diagram, it looks very easy. We have just a nice beautiful root of 1, and then it is negative, positive, so it's increasing, decreasing. It's very clear where the maximum is, but we should just write the domain. The domain of r is going to be 0 to infinity. We couldn't have a negative radius if we wanted, so we put here 0, and we cross off the rest because it's not in the domain. So clearly r is equal to 1. We can solve for h. H we know is equal to pi plus 4 minus 2r minus pi r over 2, which is pi plus 4 minus 2 times 1 is 2, and then minus pi over 2. So the pi's actually cancel, which is again wonderful, and we just end up with 2 over 2, which is also 1. Again, like I mentioned, there tends to be symmetry to these types of problems. Not always, but often you'll get symmetrical arguments like that. And so our final answer, we could say the dimensions that allow for maximum light are r equal to 1 meter, h equal to 1 meter. And there we have the solution to our problem. So let's look at one final problem here. We have a right circular cylinder to be inscribed in a sphere of fixed radius a. Let's find the dimension of the cylinder that would make the cylinder have maximum volume. Okay, well this is a little weird. Well, we've got a cylinder inscribed in a sphere. So that means there's a sphere, and there's a cylinder that's been created to, I guess, touch the sides of the sphere so that it's inside of it. And we need to make that cylinder have maximum volume. Now this question is definitely challenging. This is one of the most challenging you'd look at, partly because there's almost no information. All you're told is that the sphere has a radius of a, and somehow that needs to be enough information for you. The key is going to be to create some information by drawing your diagram in a clever way. Now, the cylinder clearly has a height of h and is going to have a radius of r. And I guess I could maybe go like this, and you start to see a bit of a triangle forming, and this is what we want to do. I drew this dot right here in the center because this is the center of the sphere. And anytime you go from the center of the sphere to the outside, you get a radius. So this would be a radius, or this would be a radius. But I want to draw this radius right here. Now my picture's not perfect, but this portion here should be the cylinder and the sphere all touching at that edge point. And so if I draw it like this, the reason why I want to do that, this is the radius of the sphere, is that I then am able to draw a small triangle. And so what I have now is, well, a little triangle that relates A as the radius of the sphere, R, and this won't be H, but it's actually going to be half the height of the cylinder, so H over 2. It's going to be very, very useful for me because that's going to create a formula. A squared is equal to H over 2 squared plus R squared. Or A squared is equal to H squared over 4 plus R squared. Now we're getting a bit ahead of ourselves because what are we trying to do? Well, we're trying to maximize the volume. So the volume of this cylinder would be pi r squared h. So this is what we want to maximize. And of course, you can see we do not have one variable. We have an r squared and an h squared, or and an h. So we need to substitute one of those in. And in this case, I think it's actually easier to plug in r squared because r squared is almost isolated right here. We got almost all the way. If we were to move this to the other side, we would get r squared is equal to a squared minus h squared over 4. Well, let's plug that on in. So volume is equal to pi a squared minus h squared over 4 times h. So we can do a little bit of math here to clean that up, a little bit of algebra. Pi a squared h minus pi h cubed over 4. And because we don't have actually any numbers, we're a lot quicker on the setup. We're ready to go. There's not really any adding, any multiplying that we have to do. We just put letters next to each other and we're ready to do our calculus. Now the derivative here is a little tricky. We do have to keep in mind that a is a fixed radius, which means a is a constant. So pi a squared h is okay to do a derivative of because the a is a constant. So the derivative of this is actually just pi a squared times 1, which is just pi a squared. Over here we're going to have 3 pi h squared over 4. Alright, let's try to set this up so we can do our sign diagram. So we're going to factor out, well, I'm going to factor out, first make common denominator, so this would be over 4 times 4. So I get 4 pi a squared minus 3 pi h squared over 4. There's that pi I want to factor, so pi 4a squared minus 3h squared over 4. And I can do my old difference of squares here. So 2a minus root 3h, 2a plus root 3h over 4. Alright, so I'm going to have two different values here. Oh, maybe I should figure out what they are. I'll do that underneath still. We'll set both of those factors equal to 0, so you'd have 2a minus root 3h equals 0. So 2a equals root 3h. So h equals 2a over root 3. And over here you'd have 2a plus root 3h. So you'd have 2a equals negative root 3h. So h equals to 2a over negative root 3. Alright, so we have our 2 points that we can use on our sign diagram. 2a over root 3, negative 2a over root 3. So pick a value bigger than 2a over root 3. I guess you can't really say 10 because we don't know what a is. But if you look at this, when you pick a bigger value, this h, because there's a negative in front of it, is going to make a negative factor here and a positive factor here. So we have a negative here, then positive, then negative. Decreasing, increasing, decreasing. Now, of course, we need to write the domain. So the domain of h would be 0 to infinity. So right here, we can cut it at 0. And the rest of all this is not in the domain. Well, it looks really clear where our maximum is happening. We're getting h equal to 2a over root 3. Let's go ahead and find our value for r. We knew, of course, that r squared was equal to a squared minus h squared over 4. So we'll get a squared minus 2a over root 3 squared over 4. Yikes, that's a bit messy, but we can work on that. So we'll get here a squared, and then we'll have minus 4a squared over 3 over 4. So the 4's actually cancel, and we get a squared minus a squared over 3, which would be 3a squared minus a squared over 3. So 2a squared over 3. And that is our value for r squared. So therefore, r would be equal to the square root of 2a squared over 3, which is, well, square root 2a over square root 3. Or if you were to write it another way, root 2 over 3a. So we have our final values, and we could say the following. The dimensions that maximize volume are h equal to 2a over root 3 and r equal to root 2 over 3a. Now, this question is definitely challenging because it's in the abstract. We have an a that carries through the whole question. But if you were actually designing something, you probably wouldn't want to use specific values because you might have to do a version of this, and then your company comes back to you and says, well, actually, you know what? We need to change the sphere that we're doing this in. We're going to make the sphere a little bit bigger, and then you have to run the math again. Then they say, no, actually, we heard from the manufacturer they can't make the sphere that big. We're going to have to make it a little bit smaller. They might be constantly changing values on you and your company, and you keep getting frustrated having to do the same maximum problem over and over and over and over. And so what you do is you get tired and you say, you know what? Eventually you're going to come to me with a radius, and I don't know what it is, and you don't know what it is. So I'm going to put it in as an A. I'm going to work the problem in general, and then I'm going to give you your formulas. This is what H needs to be, this is what R needs to be. And whenever you figure out your radius, you just plug it on in, and then if you decide to change it, you can plug it on in again. You've solved the general problem. You've made a general formula for the company, and now you can move on because whenever they decide on the radius, they can plug it in. So it's actually quite a powerful technique, especially if you're dealing with changing values in a company, or if they're going to have a whole line of products with different radii, because what you're going to do is your formula solves all of those problems all at once. So for homework, make sure you try the minimum maximum worksheet. There's a lot of questions there, 1 to 22. All the answers and solutions are there. But again, if you get stuck, you're more than welcome to ask me in one of our Google Meets, and we can take a look at some of those solutions to those. We'll also have one more set of min-max, the min-max additional questions. So those, we'll try to have you do them on your own, and then you can watch the videos for those. So until next time, thanks for watching.